we had the basis of autonomous driving down, we went in two directions. One was to do more military off-road driving. That's the Demo B panel that will follow. The other one is the Department of Transportation came to us and said, what could you do for the Department of Transportation? We have, this is me. We have, besides myself, 3 panelists. Todd Jochem. So Todd was one of us. He was a graduate student building things on the Nav Lab and started a couple of successful companies and sold them, then switched over to become a football coach. Backstory, when we were recruiting graduate students, Takeo Kanade came in and said, I found someone with a 4.0 GPA who's a football player. He plays quarterback. I think that's an important position. And that's how we decided to admit Todd to the robotics PhD program. We have Richard Bishop. Oh, and now he's back doing more computer science things. Richard Bishop, who funded us doing a lot of the work for the DOT, he went to the dark side and ran a competing program for the Urban Challenge, but he has been a consultant and a widely regarded consultant and author who really has a better finger on the pulse of the automated vehicle business than anybody that I know. We're pleased to have him join us. And Dirk Longer, who was also one of us, built radar systems, did parallel parking, and then went off to places like Audi, where he again went to the dark side and worked for Stanford on their Urban Challenge. We're happy to have Dirk back as an insider in the business. So, why automated highways? Around 1990, they were looking at problems with more and more cars, more and more accidents, more and more congestion. Who are you going to call? Automated highways. This is what the vehicle miles traveled curves looked like up until about 1990 when they were making these decisions. Now, it hasn't panned out quite the way that those projections were. It flattened out for a while, but still the overall trend is up. More and more vehicles on our highways. Here's what the trends in red, thank goodness, fatalities have dropped. But if you look at the green line, that was injuries, and that has trended back up. If you look at total accidents, they keep trending up. How has it continued since then? Well, good, the fatalities have dropped back down again. Injuries peaked and then dropped back down. There was sort of the sense that we got as far as we could with better cars, crumpled zones, etc. We got as far as we could with better highways. The interstate highway system was being completed. We got as far as we could with better laws, drunk driving. But there were still problems going on. We needed to address them. And one of those problems was congestion. Look at the trend in billions of gallons of fuel wasted, and that trend has continued to go up. So how are you going to fix all of these things? Well, first of all, how are you going to fix safety? The most dangerous part of a car is the loose nut behind the wheel. Most accidents, close to 90%, are caused at least in part by the driver. We can't do much more to make smarter drivers. Let's make smarter cars. Commonly held that you can't build your way out of congestion. If you expand the roads, I disagree with this one a little bit. I heard a talk saying if we add one more lane, that will attract traffic from other roads, it will attract traffic from other times, it will attract traffic from other modes. My answer was great. All you have to do is add one lane, and that means that other roads are less congested and other times are less congested. They didn't like that answer. But there are clearly places like downtown LA, you don't have room to build more lanes. The average American won't walk more than 800 feet. If you're going to build public transit, you're going to have to build public transit that has an awful lot of stops or has personalized shuttles or something like that. So how do you solve this? Well, first of all, the National Highway Traffic Safety Administration said, let's work on the kinds of accidents that there are. There are accidents where you sideswipe somebody changing lanes. There's accidents where you run into somebody in the rear end. These tend to be pretty survivable. And Carnegie Mellon, could you work on runoff road collision countermeasures? There's not that many runoff road accidents, but if you run off the road and you wrap yourself around a tree, they're disproportionately fatal. So how would you go about solving that one? This was Dean and Todd working on this one. How do you approach it? Well, what causes runoff road accidents? If they're caused mostly by tires blowing out, then building a smarter car won't help. It turns out they're mostly caused by people. If it's mostly going too fast, that's one thing. If it's mostly being distracted, that's something else. It's mostly distracted, just drifting out of the lane and a straight road. I collect stories of the strangest things that people have encountered on the roads. What's the strangest thing that you've encountered on a road? I love the toilet one. Guy going down a road and a toilet fell off the truck in front of him. You think about a toilet, it's ceramic. That's what they make stealth out of. It's not going to reflect radar. Laser is going to hit it and reflect off specularly. I asked him what happened. He said, all I remember is shards of porcelain flying all over the roadway. What does a typical accident scene look like? In order to figure this out, you got to figure out if you ran off the road and there's no shoulder anyway, then you don't have enough time to warn somebody. If you've got a 6-foot shoulder, now you've got enough time to warn people. If you could warn a driver, how would they react? We got some time on the Iowa driving simulator, which is like a flight simulator. Put a driver in there, have them driving down the simulated road, ask them to look for the Frank Sinatra tape, and there isn't a Frank Sinatra tape. And while they're looking down, you input a simulated wind gust. Now they're drifting out of the road. Now you can do things like beep at them or shake the steering wheel. In the US, if you nudge the steering wheel, they took the hint and they nudged it back. In Germany, when our friends at Daimler tried to do the same thing and they nudged the steering wheel, a German driver said, "Nein," and pulled the steering wheel the other direction to counteract the bump they thought they just hit, thereby pulling the vehicle further into the ditch and causing a worse accident. So you have to understand the human factors. Once you understood all of that, the context and the human factors, et cetera, now you can go out and start collecting how do people actually drive. And that's what Parag was up to. Now you can start to say, do you have to have maps? Now you can start to say, how well do drivers really drive? Do they drive differently when they're fatigued? Then you can start to build all of the vision systems, et cetera, that you need to warn drivers. How about the full automation thing? We ended up in a consortium with GM and Delco as the car companies, Parsons, Brinkerhoff, and Bechtel talking about the roads, Lockheed Martin doing systems engineering, Caltrans, which owns the highways in California, CalPath and CMU. Todd wanted me to put CMU before Berkeley. I said I saved the best for last as the system providers and getting ready to build a vehicle. There is precedent that GM in the 1950s built this cool vehicle with turbine engines and swoopy tail fins, and it actually had an automated highway following system that could follow a buried cable. If we have time during Q&A, we can come back and show the video here. So what do we have to address? If you automate all of the vehicles, is that going to decrease congestion, or is that just going to mean that everybody's going to live twice as far from their work as they do now, and you've just increased urban sprawl? Should we have the federal government deeply involved in this so that they can set a policy for things like urban sprawl, or is this up to the car companies? Berkeley had a dedicated lanes, only automated vehicles go in these lanes. That works if you're in Berkeley and you've got 6 lanes going each direction. It doesn't work in Pittsburgh, where other than the Parkway, you only have 2 lanes going one direction, and you couldn't take a lane away to be dedicated. If you have this double the number of vehicles traveling down the road and you dump them into downtown, where's all the traffic going to do? Do you need to have an off-ramp that goes directly into an automated parking garage? Should we automate buses and trucks? Can we do something to the infrastructure to make it better? What do we really need to fix? Do we need to be able to determine ice? Do we need to be able to determine stopped vehicles? All those kinds of things. And how do we impress the public with the demo? So what do I think we learned? And Todd will show the video, which will show you the technical content behind all of this. What have we found from all of our work with DOT? The runoff road collision countermeasures really work. During the time that I was working on this, I lost 5 friends, including our graduate student Ivan Ulrich and his wife, in collisions that could have been prevented by runoff road countermeasures. The fact that that technology is out there on today's cars is of great personal satisfaction. The Berkeley people wanted to have dedicated lanes. That has not panned out. Individual vehicles, really smart, full of sensors, seems to have won. Full automation will get there maybe in special applications like ports. And I think we're going to have a panel argument over this. Eventually. 30 years ago, I said, when people asked how long it would be before this stuff worked, I said, I will retire when I can drive into retirement in a self-driving vehicle. And I haven't retired yet. That's kind of the background and where we were. Todd, come up and talk to us about the technology.
Okay. Well, first off, I've been out of the industry of self-driving cars in particular since, wow, 1999. So I was thrilled when Martial invited me back. It's a special place. Those young people back there, I think, don't understand it yet, but Carnegie Mellon is very unique and a very special place to be if you're going to do robotics. Obviously, the people. And coming back today to see everybody has been incredible. Also, kind of the ethos. You know, there's not many places in the world that you can get a PhD, at least when I was coming in, for building Ambler, right? Building something, for doing systems integration, for building a radar. Carnegie Mellon, because of its history, has always valued applied research, and I think that's very unusual this day and age. Certainly back then it's unusual, and I think it still is. Great place for that. Also, the administration, and I wish the president was still here, but I was thinking on the flight, what exactly did Chuck and Takeo say to the president back then and the board when they were going to him say, hey, we've got these guys who are going to take this autonomous vehicle on the highway at highway speeds? What did they say to convince them to not endanger our multi-billion-dollar endowment? Yes, yeah, I think because we were in the car. So our administration has always been that supportive. And finally, the reputation. I've told thousands of students the best 6 letters in the alphabet are CMU PhD. And I truly believe that from the bottom of my heart. No matter what I've ever done in life, whether it's football or robotics or whatever, those 6 letters have always been very important to me and are extremely valuable. Finally, I think today in here, and I wish Hans was here, Hans Moravec, we span in this room nearly the entire history of self-driving cars, from SRI and Stanford with the Stanford Cart and Shaky, CMU Integrator and NavLab, which Chuck showed, and I'm going to include AHS in that. And then we go to Red's Grand Challenges that kind of carried the weight in the 2000s. And that mantle has sort of been taken over now by Tesla and all the other car companies that are based on, yeah, we can do this. Now, whether they're true or not, I don't know, but that's what they're moving forward. But the point being, right here, right now, maybe is the only time in history when we can look back and have people touch the beginning and also have people that are touching the forefront. So it's a very special time. All right, with that being said, I'm going to talk about the automated highway system free agent demonstration. No infrastructure, all the sensors are on the cars. We were teamed up with a great group of guys from Houston Metro. True Texans in every sense of the word, and they were great to work with. They contributed some buses. The 3 vehicle types were buses, 2 sedans, and a minivan. Had all the functions that you see on modern cars now, 360-degree sensing, warning and avoidance, we made our own digital maps because they weren't good enough then. Obviously, our actuators on the steering wheel, throttle and brake, driver interfaces, and we even had early versions of Wi-Fi for vehicle-to-vehicle communications. The goals back then, and this is actually the presentation from 1997 that I just added to. The goals were incremental deployment. All right, well, that sort of happened with warning systems and supervised full self-driving, which I guess is what Tesla calls it, beginning in the late 2000s and certainly into now. There are near-term benefits was a goal. Adaptive cruise control, lane departure warning are obvious ones, and that's a decade or more old. A goal was to use the same technology on multiple vehicle types, and there are literally hundreds of vehicles now, from the least expensive to the most expensive, that have this technology. And another one that we pushed hard was, let's not build new roads. Let's let everyone live near potential AHS. And Chuck was more modest, but I think the battle's over. We're not going to have dedicated lanes anytime soon. And it's all been the free agent singular vehicle type solutions. There are the 5 vehicles, 40-foot transit buses, minivan, 2 sedans. Technology was very similar to what's in every car now. We had cameras, we had radar. There were lasers on the buses. Audible alerts. We had our own DGPS base stations, which sort of isn't needed anymore now. All the internal sensors like gyros, roll pitch yaw sensors, safety takeover technology, like you grab the steering wheel and you have control back, you tap the brake, you have control back. All of that were on these vehicles built in 1996 and used in 1997. The inside of the car, besides the system display in the middle, was identical to what was a stock car back then. I guess the head-up display was used on some Cadillacs. The guys at Delco did a nice job integrating an early version of a flat panel display into the dashboard, as well as audible alerts and feedback, and they put some special buttons on the steering wheels for us. So it was very, very slick for a 1997 vehicle. Now, the trunk is very interesting, and you can ignore everything in there except all of these vehicles and all of the capabilities was powered by one Pentium Pro computer running QNX operating system and less than 70,000 lines of C code. Now, I'll have to say it may have been very poorly commented code without many safety checks, but it was a very compact code base doing all the steering, throttle, and brake. You'll see this more in the video, but this is essentially what the system did. It used a radar to look out at the road ahead. It used a vision system to figure out where the lane markings were, or where the lane was, not so much the markings. It would integrate those two together and then make decisions about how to stay safe in its lane, both with the steering wheel and the throttle and the brake. In the picture, you can see the axis and the yellow and green axis, or the radar. You can kind of tell the outline of the road. And as you can see in the picture, and we kind of paid homage to the NavLab with the little blue truck looking thing, it actually could see what was around it. The side radars would tell you if there was a vehicle next to you so it wouldn't change lanes automatically. It was able to detect obstacles, and we did set up a technology where it would pass through this early version of Wi-Fi to vehicles behind it. There was an obstacle there, so they could actually change lanes without seeing the obstacle, and we'll see this in the video. All in all, it was very successful. Of the, 100 runs we did, 91 were successful. The buses over this 8-mile track in San Diego, California, were 40 for 40. 99% of the people miles were successful, and I think, 800 demo riders and 1,500 total riders, including the test sessions. In that, 2 or 3 week span, we tested and drove over 12,000 miles with 5 vehicles. And since the statute of limitations has now ended, we didn't crash, unlike some of the other teams. Richard, you're welcome to explain that more. Areas for improvement back then. Complete obstacle coverage. Now, I said it was 360 degrees. It was. but the sides and the rear were very coarse radars that had maybe 1 or 2 beams, so it was very coarse, you couldn't tell. The forward radar had 8 beams, so it wasn't very well localized like it is now, so that was an area for improvement. Also, like now, vision in harsh conditions. You know, I was amazed, frankly, at some of the things Dean did with Alvin and Ralph and how he did the vision processing was incredible. But if you can't see, you can't see, at least in the visible spectrum. So things like fog back then, clearly a problem. That would still be a problem now. And obstacle detection. Larry, can we detect negative obstacles yet? Never, exactly. So that continues. That was a problem then and continues to be a problem now. So having said that, though, I have a Tesla, and when I go on the highway, I legitimately can put it in cruise control, auto cruise, whatever they call it, and I do feel more relaxed in that situation. And maybe it's because of my background and I trust it, but I think they've largely, for normal traffic conditions, done a really good job solving that problem. On the other hand, you're nuts if you hit that button when you're on state roads or in city driving. I'm scared to death whenever I get in the car, and I don't even do that in the city. So I think there's still a very, very long way to go with these technologies before Chuck can drive off into retirement. Okay. So the video I'm going to put up is sort of a video I edited to make it shorter. I'm going to try and do it here myself. Of the AHS demo. At the end, Chuck, you stole my thunder. I put in the obligatory picture of all of you guys in the back of the nav lab. But is Ryan Stentz here? Ryan, did you see your dad in the picture? Okay. All right, I may need help. Automated highway system. There we go. Short. Does this have sound? Okay. With a variety of sensors to see the road, traffic, and obstacles around it. It has a radar buried in the front bumper, a miniature TV camera mounted behind the rearview mirror, a GPS satellite positioning antenna on the roof, a LiDAR to look for traffic behind and in adjacent lanes, and sensors for vehicle speed and heading. As I drive along, I turn on the intelligent cruise control and the NavLab 6 keeps a safe distance from the car ahead automatically. The computer systems are constantly watching the road and its surroundings. Ralph, the vision system, tracks the road by looking for lane markings and any other features which are high in contrast and parallel to the road, such as shoulder edges or pavement joints. The radar on the NavLab is an advanced model. Unlike most automotive radars, which only measure range to other vehicles, this radar can also measure relative speed and bearing. When the computer puts together the road location from Ralph with the target locations from the radar, it can determine if another vehicle is in its own lane, the next lane, or on the shoulder, even when the road is curving. When I hit the interstate, I switch the NavLab into autonomous mode. It is constantly monitoring the position of other vehicles around me and keeping an internal model of what they might do and how it needs to maneuver for safe, defensive driving. As we travel, the NavLab 6 detects other smart cars and buses. Since those vehicles drive more predictably and communicate with each other by radio, the NavLab can close up the gaps with those vehicles. As the NavLab drives around a curve, its radar sees an obstacle, and the vision system correctly detects that the obstacle is in its own lane. It also radios a warning to following automated vehicles so they can make a safe maneuver before they even see the obstacle. All right, so the question I have, Tony and Chuck, who is that? We know? Larry? I thought Larry. It looks like Carl? All right, we'll have to find that out. All right, in any case, that's all I have. Thank you guys very much. Chuck, back to you. All right.
Good afternoon. I'm Dirk Langer, and I wanted to thank you for the invitation to present here at the panel. And it's really great to be here and see old friends and colleagues. So our panel is on the automated highway systems demo in 1997. And I thought maybe I'll put that a little bit in a historical context. And in fact, the vision for automated cars is really almost as old as the automobile itself. And so the first attempts at radio-controlled cars actually happened in the 1920s already. And moving further, specifically in the context of automated highway systems, there was actually an exhibition in 1939 at the World Fair by General Motors that introduced a vision for automated highway systems.
And now we see an enlarged section of 1960s express motorway. Along the ledge of this beautiful precipice, traffic moves at unreduced rates of speed. Safe distance between cars is maintained by automatic radio control. Curved sides assist the driver in keeping his car within the proper lane under all circumstances. The keynote of this motorway, safety. Safety with increased speed.
So this was 1939 with the vision of it being available on public roads. Actually, let me go back. On public roads in 1960, so 20 years later. And then in 1956, there was another actually large advertisement by an electric company to advertise autonomous driving on a highway. And again, this was envisioned to be publicly available 20 years later in 1976. And it's interesting to note, if you look closely, you see a family of 4 in a car. The driver turned around and playing Scrabble as they moved down on a guided highway lane. And this car still has a steering wheel, whereas today sometimes people envision that fully autonomous cars actually won't even have a steering wheel anymore. And then, of course, 1976, that didn't really happen yet, but there have been continuous attempts to improve the safety of automotive and automated driving. So in Europe, there was a project called Prometheus that ran for 10 years from 1985 to 1995 to also automate driving functions and increase safety. And then starting in 1994 to 1997, we had the US DOT Automated Highway Systems project. And yeah, Todd already presented what we accomplished during that time. And the AHS project was a really important milestone in that line of automated driving. And in fact, the key accomplishments for the AHS demo was that we demonstrated level 2 autonomous driving. And we developed the technology foundation for today's autonomous driving systems. In the sensors, we already had camera, radar, LiDAR, and GPS, and real-time image processing with neural networks. And the basic autonomous driving functions for the free agent demo was lane keeping, lane departure warning, intelligent cruise control, lane change maneuvers, obstacle detection and avoidance, and vehicle-to-vehicle communication. For guided vehicles, the demonstration used magnetic nails in the roadway and radar reflective strips. However, as Chuck also mentioned, these technologies have not been really pursued afterwards, and so far the free agent has won out. So where are we today? After the DARPA challenges, the automotive industry became much more interested also in pursuing and putting effort into autonomous driving. And together with the Society of Automotive Engineers, SAE, developed a concept of 6 different levels of automated driving, towards automated driving. And starting with level 0, which is driver only, through to level 5, which is fully autonomous driving. So Automated Highway Systems Demo 2 was here at level 2, where we had already longitudinal and lateral control, but the driver still had to supervise. So the expectation is that there was a safety driver behind the wheel that at all times was fully aware of what was going on. And in the industry, advanced driver systems today are very widely available, not just in upper-end luxury cars, but also in medium and lower-end cars. We today have level 2 production cars like the Tesla or from Mercedes and GM. And we have the introduction of level 3 production cars, which mostly at the moment still run at lower speeds for safety reasons, which is traffic jam assist up to 40 or 60 kilometers per hour. So level 3 actually means that the car can autonomously drive under certain conditions, but the driver still has to be available to take over when the system cannot perform anymore. And there's discussions in the industry whether level 3 is something that should be implemented, or whether we should directly go to level 4, which is automated driving in specific environments, and the driver is not required to take over. But the automated driving is limited to very specific environments. So there are car companies that have introduced level 3 driving, and it remains to be seen how well that will be accepted. The issues that can occur with level 3 driving is, of course, there's legal restrictions, but because the system is already at a quite high level of automation, but if it fails, the driver is required to take over, then how do you ensure that the driver actually can take over? That the driver is still awake, for example, hasn't dozed off or is distracted with other tasks. And we call this in the industry operator fatigue or automation complacency. If the driver is in a state of mind where he cannot or does not expect to take over. So this is for personal vehicles. We, of course, do have companies already that have built level 4 custom-built vehicles for taxi services. And the examples here are Waymo and Cruise. So these are fully driverless vehicles that can drive in specified environments without any driver interaction. In terms of outlook for the industry, auto industry, for level 4 production cars, for personal vehicles, there's a cost factor, and myself having worked in the industry for the last 15 years, automotive is really driven by cost, and the amount of hardware that is required is still, I would say, it's still not at the level yet where you can actually sell it in a vehicle. And you need to also ensure reliability, especially of sensors. We are slowly getting there, but it's not quite there yet. So this will probably take still a considerable number of years before we get to a level 4 production cars. And then level 5, which is autonomous driving pretty much everywhere, at least for personal vehicles. That may be a very long time in the future. Thank you very much.
Well, hello, everybody. I am deeply honored to be here because I'm not from this community. I'm, an outsider who happened to intersect with Carnegie Mellon during those heady days of the 90s. And I've stayed with the autonomous vehicle world ever since, been really surfing the wave as it cranked up. So I'm going to give you a feeling for where we are today. Thank you. But before I do that, I'll comment on some of this history we just heard. What hasn't been talked about is how did this idea of USDOT doing an autonomous vehicle activity even occur? It did not bubble up within the existing USDOT. It came from Congress. So this all started in 1991 when the Berlin Wall had just come down and Congress was moving money from defense over into civilian things because this was the end of war, right? We're done with all that. And somehow, some way, the chief scientist in one of the congressional House committees said, wrote it down, the Department of Transportation shall develop and demonstrate an automated highway system and shall demo it by 1997, which was the end point of that legislation. This was the authorization bill for USDOT for covering the next 6 or 7 years. That's how it showed up. What also showed up in 1991 in USDOT was me. I had been in the defense world, National Security Agency, doing things, and I finally, the glamour of all that top secret stuff wore off after a while, and I wanted to do something civilian. I went to a federal job fair at the Shoreham Hotel in Washington, all this stuff around. I thought maybe NASA or something. And back in the back corner was the Federal Highway Administration with talk about intelligent vehicle highway systems. I thought it was cool. I took the job. There I was. How did I get here? I'm a DOD guy. But what happened was this program came in, and I was the one double E amidst a sea of civil engineers. And here's this high-tech thing, and they say, Bishop, you know something about this GPS thing, and you knew something about system engineering. You're the guy. Serendipity, right? The way things can happen in our world. And I'm very grateful. It's been a great ride. So where are we now? What we'll do in the panel is talk a little bit about how much the AHS program actually affected where we are now. But just to give you a quick overview, the big picture here, we're talking about outdoor autonomy. You can see that we've got lots in the warehouse, but everything else in my image here is in the outdoor world. Wherever the vehicles are working, doing work, trucks, cars, whatever, there's a need for autonomy because there's a huge driver shortage. I'm going to talk about personally owned vehicles real briefly and then get into a couple of other topics. And Dirk covered a little bit of this, but the level 3 is moving in very quickly, and this is a big deal because level 3 says you can take your hands off the wheel and you can take your eyes off the road, which means this is the first time in the history of automobiles that you can do something else with your brain while you're in the car in the driver's seat. And I think most drivers, as they experience this, it will be like full autonomy because these vehicles are going to run for, a very, very remote chance of an intervention needed. So this is a big deal. It is on the market now from Mercedes in both Germany and California and on approved roads. It's coming from others soon. So that's pretty much all I want to say about that. The personal vehicle activity, it's great, but the real action is in fleet operations. Why is this? With a personally owned car, that car has to work anywhere the customer wants to take it. That's not true with fleet operations. So you can choose the operational design domain as you needed. Of course, the cost pressure is not the issue. It's return on investment. And you can have maintenance staff, rework, revalidate that system every day if needed. And so in this world, this is where the action is. No doubt you've heard about the robotaxi scene. Several companies there. How many of you have ridden in a commercial robotaxi? Yeah, I figured there'd be a bunch of hands. Waymo is really out there. There's several others, Cruise and Zoox. And the numbers coming from Waymo these days, 150,000 paid trips per week across a few cities. 25 million rider-only miles, as they call it. They're adding 4 million miles a month. Mind-blowing when you go back to the 1990s and think about this. And now they're adding highway operations, which makes sense. and starting to partner with Uber, which makes this just much more open to the public. Driverless trucks, lots happening here because this is all about the money. You don't have a retail customer. You've got a business-to-business activity going on. There's 4 trucking domains that I talk about: long haul, short haul, logistics yards, sort of behind the fence, and industrial operations. And looking at those first 3, we have quite a few happening globally, quite a few startups, and then we have a lot of activity in the U.S. The U.S. is the epicenter of all of this because our regulations are so weird. The federal government, federal motor carrier regulations, if it's not specifically prohibited, it's permitted. So autonomy is not prohibited, it's permitted. Doesn't work that way in Europe and other places. That's why so much is happening. These are the players. As you see in the long haul, there's 7 companies now. You know some of them. They're moving along. One of them, Aurora, is publicly traded. Then short haul B2B is active as well, and then the logistics yard world. And then this is a really key point. You know, the startups happen, they do their thing, et cetera, but it's just a startup. How are you going to go to a trucking company and say, use my services? You'll get a little bit of a foothold, you'll get started, but what really needs to happen is you're integrating with the truck manufacturers. And even more importantly, autonomy needs deep redundancy, steering, brakes, throttle, even cooling, you know, electrical power, and that needs to be engineered in deep within the vehicle. And so to have a production deal with the vehicle manufacturer means that you can get this redundancy off the line, the manufacturing line, and then you're ready for the real world in terms of the customers out there. And a quick look at what's the timing here. We're seeing some autonomy has happened already on the bottom row there, the industrial operations, but 2024 is where we're seeing full autonomy, driverless operations in the yard automation world, and we're seeing a lot planned to happen in 2025. I believe these are credible assertions from the different companies that this next year will be when we turn the switch and there's driverless trucks, tractor trailers, as well as straight trucks on the public roads doing work, earning revenue. So it's getting real. It really is getting real. So with that, what we're seeing in the car side, personal car, the crash avoidance and convenience systems are getting ubiquitous in the cars, and the level 3 is coming. Robo-taxis have been serving the public in a huge way. A lot of exposure to people, and about, my count is 5 million residents of the U.S. can access a robo-taxi. And that's growing quickly. And the robo-trucks, like I said, they're in launch mode, transitioning to commercial driverless revenue generations. And then now it's about scaling. It's not about test and development, no more science project. It's about creating, deploying a business, a service, and really making it work. So that's the end. If you really want to geek out on this topic, you can write to me. I think it's important to say also that it's a bit of a miracle that we got this far. Of course, the military would have continued developing autonomy, but what about the passenger car world? That's a completely different world, and how did this happen? And I would say that the original miracle of autonomy is after the last challenge, DARPA challenge, the Urban Challenge, a guy named Larry Page at Google heard about it and thought it was cool. And he set up a team. And he funded this team. And if that hadn't happened, because what happened after that was other investors said, oh, this idea of hardware and software on roads, which would have freaked them out completely before, well, Google's doing it, so we'll do it. And the whole waves just started crashing on the shore about all of that. So if Google hadn't have done that, we might still be 20 years away from everything I just talked about. I call it the original miracle of autonomy. So let's start talking about it. Thank you.